In the vast cosmic theatre, few events are as spectacular or as violent as the death of a massive star. These stellar giants, born from the gravitational collapse of enormous gas clouds, live fast and die young in astronomical terms. While our Sun will burn steadily for about 10 billion years, a star with 8 to 25 times the mass of our Sun races through its entire life cycle in just a few million years. Their story is one of constant battle between two fundamental forces: the outward pressure from nuclear fusion in their cores and the relentless inward pull of their own gravity. To understand how neutron stars form, we must first journey into the heart of these stellar behemoths during their final moments. Picture a star 20 times more massive than our Sun. For millions of years, this giant has maintained a delicate balance. In its core, temperatures soar to over 100 million degrees Celsius, hot enough to fuse hydrogen atoms into helium, releasing tremendous amounts of energy. This energy creates radiation pressure that pushes outward, counteracting the star's own gravitational pull, trying to collapse it inward. But massive stars are voracious consumers of fuel. Unlike our Sun, which will spend billions of years slowly converting hydrogen to helium, these giants burn through their nuclear fuel at an incredible rate. The more massive the star, the hotter its core becomes, and the faster it consumes its fuel. It's like comparing a small campfire that burns all night to a roaring bonfire that consumes logs in minutes. As the hydrogen in the core becomes depleted, the star faces its first crisis. Without the outward pressure from hydrogen fusion, gravity begins to win the battle, compressing the core. This compression heats the core even further, eventually reaching temperatures of several 100 million degrees. At these extreme temperatures, a new type of fusion becomes possible: helium burning. 3 helium nuclei can now fuse together to form carbon, releasing energy and temporarily restoring the balance between gravity and radiation pressure. This process repeats in a cosmic cycle of boom and bust. When the helium runs out, the core contracts and heats up again, reaching temperatures where carbon can fuse to form neon and magnesium. Then neon burning creates oxygen and magnesium. Oxygen burning produces silicon and sulfur. Each successive stage burns hotter and faster than the last, like a car engine racing toward its red line. The star during these final stages resembles a cosmic onion, with shells of different elements arranged in layers. The outermost layers still contain hydrogen, while deeper shells burn helium, carbon, neon, and oxygen in sequence. At the very center, silicon burning produces iron and nickel. This layered structure is crucial to understanding what happens next, because it sets the stage for one of the most dramatic events in the universe. Silicon burning represents the end of the road for nuclear fusion as an energy source. When silicon fuses, it creates iron-56, the most stable nucleus in the universe. Iron-56 sits at the bottom of the nuclear binding energy curve, meaning it takes more energy to fuse iron nuclei together than you get out of the reaction. For the first time in the star's life, nuclear fusion becomes an energy sink rather than an energy source. This is where the story takes a dramatic turn. Without the outward pressure from energy-generating fusion reactions, gravity finally wins its long battle. The iron core, typically about 1.5 times the mass of our Sun but compressed into a sphere only about 3,000 kilometers across, suddenly finds itself unable to support its own weight. The collapse that follows is almost unimaginably rapid and violent. In less than a second, the core shrinks from 3,000 kilometers in diameter to just 20 kilometers. During this collapse, the core's density increases by a factor of about 100 billion. To put this in perspective, if you could compress the entire Earth to the same density, it would fit inside a sphere just 200 meters across. As the core collapses, several extraordinary things happen simultaneously. the temperature skyrockets to over 100 billion degrees Celsius, more than 6,000 times hotter than the Sun's core. The pressure becomes so intense that atomic nuclei are crushed together, and electrons are forced to combine with protons to form neutrons. This process, called neutronization, releases vast numbers of neutrinos, ghostly particles that barely interact with matter. The neutrinos produced during core collapse carry away an enormous amount of energy, about 100 times more energy than our Sun will produce in its entire 10 billion year lifetime. Most of these neutrinos escape the star within seconds, carrying with them information about the collapse that we can potentially detect here on Earth. But the collapsing core doesn't shrink indefinitely. When it reaches nuclear density, about 2 × 10⁻14 power grams per cubic centimeter, the neutrons themselves begin to resist further compression through a quantum mechanical effect called degeneracy pressure. This is the same principle that prevents the electrons in atoms from all occupying the same energy state, but now applied to neutrons packed together at incredible density. The sudden halt of the collapsing core creates a shockwave that reverses direction and races outward through the star at thousands of kilometers per second. This shockwave is what we observe as a supernova explosion. The energy released in a supernova is truly staggering, equivalent to the sun shining for about 10 billion years, all released in a matter of seconds. The shockwave blasts through the star's outer layers, heating them to billions of degrees and accelerating them to speeds of thousands of kilometers per second. These outer layers, enriched with heavy elements created during the star's lifetime, are scattered into space, seeding the interstellar medium with the raw materials for future generations of stars and planets. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the core of a massive star and distributed by a supernova explosion. Meanwhile, at the center of this cosmic violence, something remarkable remains. The collapsed core has become a neutron star. This object, containing more mass than our Sun, but compressed into a sphere only about 20 kilometers across, represents one of the most extreme environments in the universe. Its surface gravity is about 100 billion times stronger than Earth's gravity. A sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. The composition of a newly formed neutron star is unlike anything we encounter in everyday life. The outer crust consists of atomic nuclei arranged in a crystalline lattice, but these nuclei are far more neutron-rich than any found on Earth. As you go deeper, the nuclei become increasingly exotic, with neutron-to-proton ratios that would be impossible under normal conditions. Deeper still, at densities approaching nuclear density, the distinction between individual nuclei begins to break down. Neutrons start to drip out of nuclei, creating a sea of free neutrons mixed with increasingly neutron-rich nuclei. This region, sometimes called the neutron drip line, marks the transition from normal nuclear matter to the exotic matter that dominates the neutron star's interior. At the very center of the neutron star, densities may reach 5 to 10 times nuclear density, creating conditions that push our understanding of physics to its limits. At these extreme densities, protons and neutrons themselves might break apart into their constituent quarks, creating a soup of the fundamental particles that make up all matter. Alternatively, the intense gravitational field might allow the creation of exotic particles like hyperons, which contain strange quarks not found in normal matter. The magnetic field of a neutron star is another legacy of its violent birth. During the core collapse, magnetic field lines are compressed along with the matter, amplifying the original stellar magnetic field by factors of trillions. The resulting magnetic field can be 1 trillion times stronger than Earth's magnetic field, powerful enough to distort the very atoms in the neutron star's atmosphere. This intense magnetic field, combined with the neutron star's rapid rotation, creates one of the most precise clocks in the universe, a pulsar. As the neutron star spins, its magnetic field accelerates charged particles to near light speed, creating beams of radiation that sweep across space like lighthouse beams. When these beams point toward Earth, we detect regular pulses of radio waves, X-rays, or gamma rays, some arriving with clockwork precision that rivals the best atomic clocks. The birth of a neutron star also represents a victory of quantum mechanics over classical physics on a cosmic scale. In normal matter, atoms are mostly empty space, with electrons orbiting far from their nuclei. But in a neutron star, matter is compressed beyond the point where atoms can exist. Instead, quantum forces prevent the complete collapse into a black hole, creating a state of matter where an entire star behaves like a single giant atomic nucleus. The thermal evolution of a neutron star after its formation tells another fascinating story. Born at temperatures of billions of degrees, neutron stars cool primarily through neutrino emission for the first few thousand years. These ghostly particles, which barely interact with normal matter, can escape freely from the neutron star's interior, carrying away thermal energy. After about 1 million years, neutrino cooling becomes less efficient, and the neutron star cools mainly by photon emission from its surface. The cooling process reveals important information about the neutron star's internal structure. Different theoretical models of ultra-dense matter predict different cooling rates, so observations of neutron star temperatures can help us understand what happens to matter under such extreme conditions. Some neutron stars cool faster than others, possibly indicating the presence of exotic particles or superfluidity in their interiors. Neutron stars also serve as natural laboratories for studying matter under conditions impossible to reproduce on Earth. The densities in neutron star cores exceed those achieved in any particle accelerator, while the magnetic fields dwarf anything we can create in laboratories. By studying neutron stars, we gain insights into fundamental physics that would otherwise remain purely theoretical. The formation of neutron stars represents just one possible outcome for massive stars. Stars with initial masses between about 8 and 25 solar masses typically become neutron stars, but the exact boundaries depend on factors like stellar rotation, magnetic fields, and metallicity. Stars less massive than 8 solar masses don't reach the temperatures needed for silicon burning and instead end their lives as white dwarf stars. Stars more massive than about 25 solar masses may collapse directly into black holes, skipping the neutron star phase entirely. The transition from a living star to a neutron star marks one of the most dramatic transformations in nature. In less than a second, matter that once filled a volume larger than Earth becomes compressed into a sphere that could fit within a large city. The star's rotation rate, initially perhaps 1 revolution per month, speeds up dramatically as the core contracts, with some neutron stars spinning hundreds of times per second. This process of neutron star formation connects stellar evolution, nuclear physics, and general relativity in ways that continue to challenge our understanding. Each neutron star represents a unique experiment in extreme physics, where gravity, quantum mechanics, and nuclear forces interact under conditions found nowhere else in the universe. As we'll explore in the following chapters, these cosmic laboratories continue to reveal new secrets about the fundamental nature of matter, energy, and space-time itself. The violent birth of neutron stars through supernova explosions has shaped the chemical evolution of galaxies and provided the heavy elements necessary for rocky planets and life as we know it. Yet perhaps even more remarkable is what these stellar remnants become: the densest objects in the universe outside of black holes, where gravity reaches strengths that bend space-time itself and create some of the most extreme gravitational environments we can observe. From their explosive birth in the death throes of massive stars, neutron stars emerge as cosmic beacons that will shine across the universe for billions of years, their steady pulses marking time while their extreme gravitational fields provide natural laboratories for probing the deepest mysteries of physics. When we think about gravity in our everyday lives, Isaac Newton's simple formula serves us well. Drop an apple, and it falls toward Earth at 9.8 meters per second squared. Launch a rocket, and we can calculate its trajectory using equations that Newton developed over 3 centuries ago. But neutron stars exist in a realm where Newton's gravity becomes woefully inadequate, like trying to measure the speed of light with a sundial. To understand gravity around neutron stars, we must abandon our intuitive notions and embrace Einstein's revolutionary vision of space-time itself. In 1915, Einstein published his theory of general relativity, fundamentally changing how we think about gravity. Rather than a force pulling objects together, gravity became the curvature of space-time caused by the presence of mass and energy. Imagine a bowling ball placed on a stretched rubber sheet, creating a depression that causes marbles to roll toward it. This analogy, while imperfect, captures the essence of how mass warps the fabric of space-time. In most situations we encounter, the difference between Newton's and Einstein's descriptions of gravity is negligible. Earth's gravity well is so shallow that space and time remain nearly flat. A GPS satellite orbiting Earth experiences only tiny relativistic effects, requiring corrections of mere microseconds per day. But neutron stars create gravitational fields so intense that they stretch the very concepts of space and time beyond recognition. Consider the numbers that define a typical neutron star. Pack 1.4 times the mass of our Sun into a sphere just 20 kilometers across, and you create a gravitational field roughly 100 billion times stronger than Earth's. At the neutron star's surface, gravity pulls with such ferocity that it would compress a human body to the thickness of a sheet of paper in microseconds. But even this staggering number fails to capture the true strangeness of neutron star gravity. The key insight from general relativity is that gravity is not just about the strength of the gravitational pull, but about how dramatically mass and energy curve space-time. Near a neutron star, this curvature becomes so severe that space and time themselves behave in ways that seem impossible from our everyday perspective. Time runs slower, distances contract, and light itself struggles to escape the gravitational grip. To visualize this curvature, imagine space-time as a flexible 3-dimensional grid extending in all directions. In empty space, this grid remains straight and regular, with parallel lines staying parallel and right angles remaining perfectly square. But place a neutron star at the center of this grid, and everything changes. The grid lines bend inward toward the neutron star, becoming more and more distorted as they approach its surface. This distortion affects everything in the vicinity. A photon of light trying to escape from the neutron star's surface must climb out of this gravitational well, losing energy in the process. By the time the photon reaches a distant observer, its wavelength has been stretched, making it appear redder than when it was emitted. This gravitational redshift can be so extreme that X-rays emitted from a neutron star's surface arrive at Earth as visible light. The mathematics describing this curved space-time around a neutron star are far more complex than Newton's simple inverse square law. Einstein's field equations, which relate the curvature of space-time to the distribution of matter and energy, require sophisticated techniques from differential geometry to solve. Even with modern computers, finding exact solutions remains challenging for realistic neutron star models. One of the most useful approximate solutions is the Schwarzschild metric, which describes space-time around a spherically symmetric, non-rotating massive object. For a neutron star, this metric reveals several remarkable features. As you approach the neutron star's surface, time dilation becomes increasingly severe. A clock on the neutron star's surface would tick noticeably slower than an identical clock far from the star. If you could somehow stand on a neutron star's surface for 1 hour, observers far away would measure that several hours had passed. This time dilation is not just a theoretical curiosity, it has observational consequences. When we observe X-ray bursts from neutron stars, the radiation we detect has been affected by this time dilation. Rapid oscillations in the X-ray flux appear slowed down to distant observers, providing a way to measure the strength of the neutron star's gravitational field. The curvature of space around neutron stars also affects the propagation of light in unexpected ways. Photons no longer travel in straight lines, but follow curved paths called geodesics through the warped space-time. This effect, known as gravitational lensing, means that we can sometimes see around a neutron star, observing emission from its far side that would normally be hidden from view. Recent observations by NASA's Neutron Star Interior Composition Explorer, known as NICER, have exploited this gravitational lensing effect to map hotspots on neutron star surfaces. As the neutron star rotates, these hotspots move in and out of view, but gravitational lensing allows us to see additional emission that would otherwise be blocked. By analyzing these light curves, astronomers can determine both the neutron star's mass and radius with unprecedented precision. The extreme curvature of space-time around neutron stars also affects the behavior of matter in their vicinity. Particles orbiting close to a neutron star experience frame dragging effects, where the neutron star's rotation literally drags space-time around with it. This effect, predicted by general relativity and confirmed around Earth by the Gravity Probe B mission, becomes dramatically enhanced near neutron stars. Frame dragging has important consequences for understanding neutron star systems. Matter falling toward a rotating neutron star doesn't simply spiral inward, but gets caught up in the star's rotation, forming complex accretion flows. The magnetic fields threading through this matter become twisted and amplified, sometimes launching powerful jets of particles at near light speed. When we compare neutron star gravity to that of black holes, fascinating similarities and differences emerge. A black hole with the same mass as a neutron star would have a much smaller radius and correspondingly stronger surface gravity. The event horizon of a 1.4 solar mass black hole would lie at a radius of about 4 kilometers, compared to the 10 to 12 kilometer radius of a neutron star. This difference in radius has profound implications for the gravitational environment. While both objects create significant space-time curvature, the neutron star's surface remains accessible to observation, whereas a black hole's surface lies hidden behind its event horizon. We can observe matter falling onto a neutron star's surface, study the properties of its atmosphere, and detect thermal emission from its crust. A black hole of similar mass would appear much dimmer, revealing itself mainly through the hot accretion disk swirling around it. The gravitational redshift provides another useful comparison. Light escaping from a neutron star's surface typically experiences a redshift of about 20 to 40%, meaning that blue light emitted from the surface appears green or yellow to distant observers. Light attempting to escape from near a black hole's event horizon experiences infinite redshift, becoming so stretched in wavelength that it effectively disappears from view. These differences make neutron stars invaluable laboratories for studying strong field gravity. Unlike black holes, neutron stars allow us to observe matter under extreme gravitational conditions while still remaining visible. We can study how atoms behave in gravitational fields billions of times stronger than Earth's, how magnetic fields interact with curved space-time, and how matter flows in environments where general relativistic effects dominate. The precision timing of pulsar signals provides another window into neutron star gravity. As these rotating neutron stars sweep beams of radiation across space, we receive regular pulses with timing stability that rivals atomic clocks. But this timing is affected by the neutron star's gravitational field in measurable ways. The pulse profiles, arrival times, and frequency evolution all encode information about the underlying space-time geometry. Binary pulsar systems offer particularly rich laboratories for studying gravity. When two neutron stars orbit each other, they create a dynamical gravitational environment where space-time curvature changes continuously. The orbital motion generates gravitational waves, ripples in space-time itself, that carry away energy and cause the orbit to decay. This orbital decay, first measured in the Hulse-Taylor pulsar system, provided the first indirect evidence for gravitational waves and earned its discoverers the Nobel Prize. The recent direct detection of gravitational waves by LIGO and Virgo has opened an entirely new window for studying neutron star gravity. When two neutron stars spiral into each other and merge, they create some of the most violent gravitational wave signals in the universe. These signals encode detailed information about how matter behaves under extreme gravitational stress, including how the neutron stars deform as tidal forces stretch and squeeze them. The tidal deformability of neutron stars provides crucial insights into their internal structure and the nature of ultra-dense matter. Just as Earth's oceans bulge in response to the Moon's gravitational pull, neutron stars deform when subjected to external gravitational fields. However, the amount of deformation depends on the star's internal structure and equation of state, the relationship between pressure and density in the neutron star's interior. Gravitational wave observations of neutron star mergers have begun to constrain these equations of state, helping us understand what happens to matter at densities exceeding those in atomic nuclei. Softer equations of state, where pressure increases slowly with density, lead to more easily deformed neutron stars. Stiffer equations of state produce more rigid neutron stars that resist deformation. By measuring tidal effects in gravitational wave signals, we can distinguish between different theoretical models of ultra-dense matter. The extreme gravitational fields around neutron stars also serve as natural tests of Einstein's theory itself. General relativity has passed every test we've devised, but neutron stars push the theory into regimes far beyond those where it was originally verified. The strong equivalence principle, which states that all forms of matter and energy respond identically to gravitational fields, can be tested with exquisite precision using pulsar timing observations. Some alternative theories of gravity predict deviations from general relativity that become apparent only in very strong gravitational fields. Neutron stars provide ideal testing grounds for these theories, as their gravitational fields approach the maximum strength possible without forming black holes. So far, observations consistently support Einstein's theory, but continued studies of neutron star systems may eventually reveal new physics beyond general relativity. The gravitational environment around neutron stars also affects the behavior of fundamental particles in ways impossible to study in terrestrial laboratories. The intense gravitational redshift can shift the energy levels of atoms and molecules, potentially affecting chemical reactions in neutron star atmospheres. Quantum field theory in curved spacetime predicts that virtual particle pairs can be separated by tidal forces, leading to particle creation near neutron stars. These exotic quantum effects in strong gravitational fields connect neutron star physics to some of the deepest questions in theoretical physics. How does quantum mechanics reconcile with general relativity? What happens to information when it falls into a strong gravitational field? Can we understand the microscopic structure of spacetime itself? Neutron stars provide natural laboratories where these questions might find answers. The magnetic fields of neutron stars add another layer of complexity to their gravitational environments. Field strengths reaching 10 to the 15th power Gauss, a trillion times stronger than the strongest magnetic fields produced on Earth, interact with the curved spacetime in ways that are still being explored theoretically. The combination of extreme gravity and extreme magnetism creates unique plasma physics environments where both general relativity and quantum electrodynamics play crucial roles. As we prepare to delve deeper into the specific effects of neutron star gravity, from surface conditions to core physics, it's important to appreciate the revolutionary nature of these objects. They represent the most extreme gravitational laboratories accessible to observation, where space-time curvature approaches its maximum possible value while still allowing matter to exist in a stable configuration. The transition from the broad framework of general relativity to the specific conditions at neutron star surfaces reveals how abstract mathematical concepts translate into observable physical phenomena. Every photon that escapes from a neutron star carries information about the curvature of space-time. Every pulse arrival time reflects the gravitational redshift, and every orbital measurement probes the warping of space and time around these cosmic laboratories. Understanding gravity at these extremes requires us to think beyond our everyday experience and embrace the strange reality of curved space-time, where time runs slow, distances contract, and the very fabric of reality bends under the influence of matter and energy compressed beyond imagination. Standing on the surface of a neutron star would be an experience beyond human comprehension, if such a thing were even theoretically possible. The gravitational field at the surface is so intense that it would crush any known material instantly, yet this extreme environment reveals some of the most fascinating physics in the universe. To understand what happens at a neutron star's surface, we must examine how gravity shapes every aspect of this alien world, from the behavior of individual atoms to the structure of the star's outer layers. A typical neutron star measures only 10 to 12 kilometers in radius, roughly the size of a small city, yet contains between 1.4 and 2.3 times the mass of our entire Sun. This incredible compression creates a surface gravity approximately 100 billion times stronger than Earth's. To put this in perspective, if you weigh 70 kilograms on Earth, you would weigh 7 trillion kilograms on a neutron star's surface. The gravitational acceleration reaches about 10 to the 11th power meters per second squared, compared to Earth's modest 9.8 meters per second squared. This extreme surface gravity has immediate and dramatic consequences for anything attempting to escape the neutron star's gravitational embrace. The escape velocity, the minimum speed needed for an object to break free from the gravitational pull, ranges from about 40 to 60% of the speed of light. This means that matter leaving a neutron star's surface must achieve velocities of 120,000 to 180,000 kilometers per second, speeds that challenge our understanding of physics and approach the cosmic speed limit. These escape velocities are so high that they affect the very nature of light itself. When photons are emitted from the neutron star's surface, they must climb out of this incredibly deep gravitational well, losing energy in the process. This energy loss manifests as gravitational redshift, where the wavelength of light becomes stretched as it escapes. X-rays emitted from the surface might arrive at Earth as ultraviolet light, while visible light becomes infrared radiation. The magnitude of this gravitational redshift depends on the neutron star's mass and radius, providing astronomers with a powerful diagnostic tool. By measuring how much the light from a neutron star has been redshifted, we can determine the strength of its surface gravity and constrain its physical properties. Recent observations by space-based X-ray telescopes have used this technique to measure neutron star masses and radii with unprecedented precision. The surface itself presents a landscape unlike anything in our solar system. The solid crust of a neutron star consists of atomic nuclei arranged in a crystalline lattice, but these are no ordinary atoms. The intense gravitational field compresses matter to such extreme densities that only the most neutron-rich nuclei can exist stably. Elements like iron-56, the most stable nucleus under normal conditions, become unstable in neutron star crusts, where nuclei with dozens of extra neutrons dominate. This crystalline crust is remarkably smooth, with surface irregularities limited to just a few centimeters in height. The intense surface gravity prevents the formation of mountains or valleys larger than this. Any deviation from perfect sphericity would create stresses that exceed the breaking strength of even the strongest materials imaginable. The surface is literally flattened by its own gravity to a degree of smoothness that surpasses the finest mirrors. Yet despite this smoothness, the neutron star's crust harbors incredible complexity. The outer layers consist of heavy nuclei embedded in a sea of electrons, with the nuclei arranged in a body-centered cubic crystal structure. As you descend deeper into the crust, the neutron content of these nuclei increases dramatically. At depths of just a few hundred meters, nuclei contain so many neutrons that they begin to approach the neutron drip line, where neutrons start to leak out of atomic nuclei. The pressure at these depths reaches values that dwarf anything we can create on Earth. At just 1 kilometer below the surface, the pressure exceeds 10 to the 30 power pascals, billions of times greater than the pressure at the center of Earth. Under these conditions, the crystal lattice of nuclei becomes distorted, and exotic nuclear configurations may form. Theoretical models predict the existence of nuclear pasta, where nuclei arrange themselves into rod-like, plate-like, or other non-spherical structures to minimize their energy. This nuclear pasta phase represents one of the most unusual forms of matter in the universe. Computer simulations suggest that as density increases, spherical nuclei first elongate into rod-shaped structures, then flatten into plates, before finally inverting into a foam-like structure with neutron-rich bubbles. The names for these phases, cylindrical pasta, lasagna pasta, and Swiss cheese pasta, reflect their resemblance to familiar shapes, but their properties are anything but familiar. The gravitational field strength varies noticeably even across the neutron star's small surface. The difference in gravitational acceleration between the poles and equator due to the star's rotation can be significant for rapidly spinning neutron stars. Some neutron stars rotate hundreds of times per second, creating centrifugal forces that partially offset the gravitational pull at the equator. However, even the fastest spinning neutron stars cannot rotate fast enough to significantly reduce their surface gravity, which remains many billions of times stronger than Earth's throughout. The interaction between the neutron star's intense gravitational field and its magnetic field creates additional complications at the surface. Neutron stars possess magnetic fields that can be trillions of times stronger than Earth's magnetic field. These magnetic fields, frozen into the neutron star during its formation, interact with the curved spacetime near the surface in ways that are still being studied theoretically. In the most magnetized neutron stars, called magnetars, surface magnetic fields can reach 10 to the 15th power Gauss. At these field strengths, the magnetic energy density exceeds the energy density of matter itself, fundamentally altering the properties of atoms and molecules in the neutron star's atmosphere. The magnetic field becomes so strong that it can split photons into pairs of particles and antiparticles, creating a complex plasma environment above the surface. The atmosphere of a neutron star, if it can be called that, extends only a few centimeters above the solid surface. The intense gravitational field compresses any gaseous material into an incredibly thin layer, with scale heights measured in centimeters rather than the kilometers typical of planetary atmospheres. This thin atmosphere consists of the lightest elements available, typically hydrogen and helium, though even these are compressed to densities approaching that of liquid water. Within this compressed atmosphere, atoms behave in ways that would seem impossible under terrestrial conditions. The combination of extreme gravity and magnetic fields can stretch atoms into needle-like shapes, with electron orbitals distorted far from their familiar spherical or dumbbell forms. Spectral lines from these distorted atoms appear at wavelengths significantly different from their laboratory values, providing another signature of the extreme conditions at neutron star surfaces. The thermal properties of neutron star surfaces reflect their violent birth and subsequent evolution. Newly formed neutron stars have surface temperatures of about 1 million degrees Celsius, hot enough to emit primarily in X-rays. Over time, they cool by radiating this thermal energy into space, with their surface temperatures dropping to around 100,000 degrees Celsius after 1 million years. This cooling process is not uniform across the surface. Hotspots, heated by the bombardment of charged particles accelerated in the neutron star's magnetosphere, can reach temperatures several times higher than the average surface temperature. These hotspots, typically located near the magnetic poles, create the lighthouse-like beams of radiation that we observe as pulsar signals. The gravitational redshift affects our observations of this thermal emission in important ways. The surface temperature we calculate from X-ray observations must be corrected for the gravitational redshift to determine the actual temperature at the neutron star's surface. This correction can be substantial, with observed temperatures appearing 20 to 40% lower than the true surface values. Starquakes represent another fascinating consequence of neutron star surface gravity. As the neutron star cools and spins down over time, its shape adjusts to the changing rotational and magnetic stresses. The rigid crust occasionally fractures and rearranges itself to accommodate these changes, releasing enormous amounts of energy in events called starquakes, or neutron star glitches. These starquakes can release more energy than the largest earthquakes, despite involving fractures only millimeters in size. The extreme surface gravity ensures that even tiny adjustments in the crust's structure involve tremendous forces. When a starquake occurs, it can suddenly change the neutron star's rotation rate, causing glitches in pulsar timing that astronomers can detect with high precision. The boundary between the neutron star's surface and its interior is not sharp, but represents a gradual transition from solid crust to liquid core. In the deepest layers of the crust, at densities approaching half of nuclear density, neutrons begin to drip out of nuclei and form a neutron fluid that coexists with the crystalline lattice of neutron-rich nuclei. This neutron drip region marks the beginning of the transition to the neutron star's liquid interior. Surface effects also influence how we observe neutron star mergers and their gravitational wave signatures. When two neutron stars approach each other closely enough, their mutual gravitational attraction raises tides on each star's surface. These tidal bulges grow larger as the stars spiral inward, eventually disrupting the surface layers and creating the conditions for a kilonova explosion. The strength of the surface gravity determines how easily these tidal forces can disrupt the neutron star. Stars with stronger surface gravity resist tidal disruption more effectively, while those with weaker surface gravity are more easily torn apart. By studying the gravitational wave signals from neutron star mergers, astronomers can infer properties of the surface gravity and internal structure of the merging stars. Recent observations have revealed that some neutron stars possess surface magnetic fields that are not uniformly distributed. Instead of simple dipole configurations like Earth's magnetic field, these stars may have complex multipole field structures with strong variations across their surfaces. The interaction between these non-uniform magnetic fields and the curved space-time near the surface creates intricate patterns of particle acceleration and radiation emission. The concept of a neutron star surface also becomes somewhat ambiguous when we consider the effects of the surrounding magnetosphere. Charged particles trapped in the magnetic field can create an extended atmosphere or corona that extends far above the solid surface. The boundary between the neutron star itself and its magnetospheric environment is thus not a sharp interface, but a gradual transition region, where gravity, magnetic forces, and radiation pressure all play important roles. Understanding the properties of neutron star surfaces requires sophisticated computer models that account for the complex interplay between gravity, magnetic fields, nuclear physics, and plasma physics. These models must solve Einstein's equations for the curved space-time geometry, while simultaneously calculating the behavior of matter and radiation in this extreme environment. The observational study of neutron star surfaces continues to advance, with new space-based X-ray telescopes and improved ground-based instruments. Missions like NICER have provided unprecedented detailed observations of thermal emission from neutron star surfaces, allowing astronomers to map temperature variations and constrain surface composition. Future missions promise even more detailed studies of these extreme gravitational environments. As we prepare to explore the interior regions of neutron stars, where gravity competes directly with quantum forces to determine the structure of matter itself, the surface serves as our observational window into these hidden realms. Every photon that escapes from a neutron star's surface carries information about the gravitational field, magnetic environment, and thermal conditions that exist in this most extreme of cosmic laboratories. The skin of a neutron star thus represents far more than simply the boundary between the star and empty space. It embodies the intersection of gravity, nuclear physics, and quantum mechanics operating under conditions that push our understanding of physics to its absolute limits, while remaining just accessible enough to detailed observation that we can begin to unravel the mysteries of matter under extreme gravitational stress. Deep within a neutron star, an epic battle rages between two of nature's most fundamental forces. On one side stands gravity, relentlessly crushing matter toward infinite density with a strength that grows more powerful with each passing moment of collapse. On the other side stands quantum mechanics, specifically the Pauli exclusion principle, creating an outward pressure that refuses to allow identical particles to occupy the same quantum state. This cosmic struggle determines not only the structure of neutron stars, but also provides us with a natural laboratory where quantum effects operate on astronomical scales. To understand this battle, we must first appreciate the extraordinary nature of neutron degeneracy pressure. In ordinary matter, atoms maintain their structure through electromagnetic forces that keep electrons in orbitals around atomic nuclei. But in neutron stars, gravity has compressed matter far beyond the point where atoms can exist. Instead, the stellar interior consists primarily of neutrons packed together at densities that approach and exceed nuclear density. These neutrons, like all particles with half-integer spin, are fermions that must obey the Pauli exclusion principle. This quantum mechanical rule states that no two identical fermions can occupy the same quantum state simultaneously. In practical terms, this means that neutrons in a neutron star cannot all drop down to the lowest possible energy level as they would in a classical system. Instead, they must fill progressively higher energy levels, creating what physicists call a degenerate neutron gas. The pressure created by this quantum effect is truly remarkable. Unlike the thermal pressure in ordinary matter, which depends on temperature, degeneracy pressure depends only on the density of particles. Even at temperatures near absolute zero, a degenerate neutron gas would maintain enormous pressure, simply because of the quantum mechanical requirement that neutrons avoid each other in phase space. This pressure increases rapidly with density, following a relationship where pressure grows as density raised to the 5/3 power. The strength of neutron degeneracy pressure in stellar cores is almost beyond comprehension. In the central regions of a neutron star, this quantum pressure can reach values of 10 to the 35 power pascals, a pressure so enormous that it has no meaningful comparison in everyday experience. To put this in perspective, this pressure exceeds that at the center of our sun by factors of billions. and surpasses the strongest pressures we can create in laboratory experiments by similar margins. This quantum pressure provides the only known mechanism capable of halting the gravitational collapse of a stellar core once nuclear fusion has ceased. When the core of a massive star begins its final collapse, gravity initially wins the battle decisively. The core shrinks from thousands of kilometers in diameter to just tens of kilometers in less than a second. But as the density approaches nuclear density, neutron degeneracy pressure begins to assert itself with increasing strength. The precise moment when degeneracy pressure halts the collapse depends on the delicate balance between the strength of gravity and the stiffness of the equation of state that relates pressure to density. If gravity is too strong, or if the neutron degeneracy pressure is insufficient, the collapse continues past the neutron star stage and forms a black hole instead. The boundary between these outcomes defines one of the most important thresholds in astrophysics. Current theoretical models suggest that neutron degeneracy pressure can support stellar masses up to approximately 2 to 3 solar masses, though the exact limit remains uncertain. This maximum mass, known as the Tolman-Oppenheimer-Volkoff limit, represents the point where gravity finally overwhelms quantum mechanics. Beyond this threshold, no known form of matter can resist gravitational collapse, and a black hole forms inevitably. The density gradient within a neutron star reveals how this quantum gravitational struggle plays out across different regions of the stellar interior. Near the surface, densities remain below nuclear density, and matter exists in the form of neutron-rich atomic nuclei embedded in a sea of electrons. But as we move deeper into the star, density increases dramatically, and the nature of matter undergoes fundamental changes. At the neutron drip density, roughly half of nuclear density, neutrons begin to leak out of atomic nuclei and exist as free particles. This marks the beginning of the regime where neutron degeneracy pressure becomes dominant. The free neutrons form a quantum fluid that coexists with the remaining neutron-rich nuclei, creating a complex two-component system where both electromagnetic and strong nuclear forces play important roles. Deeper still, at densities approaching nuclear density, the distinction between individual nuclei disappears entirely. Matter transforms into a uniform fluid of neutrons, protons, and electrons, with the neutrons vastly outnumbering the other particle types. In this regime, neutron degeneracy pressure provides the primary support against gravitational collapse, while the protons and electrons contribute smaller but still significant pressure components. The quantum nature of this neutron fluid leads to several remarkable properties that have no analogue in everyday matter. At the extreme densities found in neutron star cores, neutrons can form Cooper pairs and undergo a phase transition to a superfluid state. This neutron superfluid exhibits zero viscosity and can flow through the solid crust without friction, leading to complex dynamics that affect the neutron star's rotation and magnetic field evolution. Theoretical calculations suggest that different regions of the neutron star interior may undergo superfluidity at different temperatures and densities. The neutron superfluid transition might occur at temperatures around 10 to the 9th power Kelvin, far higher than any terrestrial superfluid, but still well below the initial temperature of a newly formed neutron star. As the star cools over millions of years, different layers may sequentially transition to the superfluid state. The presence of superfluidity has observable consequences for neutron star behavior. Pulsar glitches, sudden increases in the rotation rate of pulsars, are thought to result from the interaction between the superfluid neutron component and the normal matter in the crust. When the superfluid neutrons, which continue rotating at their original rate, suddenly couple to the slowing crust, they transfer angular momentum and cause the observed glitch. Protons in the neutron star core may also undergo a similar phase transition, forming superconducting Cooper pairs at temperatures around 10 to the 10th power Kelvin. This proton superconductivity would have dramatic effects on the neutron star's magnetic field evolution, as superconductors expel magnetic fields through the Meissner effect. The competition between magnetic field expulsion and gravitational compression creates complex field configurations that are still being studied theoretically. The equation of state that describes how pressure relates to density in neutron star matter remains one of the most uncertain aspects of neutron star physics. Unlike ordinary matter, where we can measure pressure-density relationships in laboratory experiments, neutron star matter exists only under conditions that cannot be reproduced on Earth. Particle accelerators can create individual neutrons and study their interactions, but they cannot create the bulk properties of neutron matter at nuclear density. This uncertainty in the equation of state has profound implications for our understanding of neutron star structure. A stiff equation of state, where pressure increases rapidly with density, produces larger neutron stars that can support higher maximum masses. A soft equation of state, where pressure increases more slowly, leads to more compact stars with lower maximum masses. Observations of neutron star masses and radii thus provide crucial constraints on the fundamental properties of matter at extreme densities. Recent gravitational wave observations of neutron star mergers have begun to shed light on these equation of state uncertainties. When two neutron stars spiral into each other, they experience extreme tidal forces that deform their shapes. The amount of deformation depends sensitively on the neutron star's internal pressure distribution, which in turn depends on the equation of state. By measuring tidal effects in gravitational wave signals, astronomers can constrain the stiffness of neutron matter. The quantum mechanical nature of neutron degeneracy pressure also affects how neutron stars respond to perturbations. Unlike classical fluids, degenerate neutron matter exhibits complex oscillation modes that depend on quantum statistical effects. These stellar oscillations, triggered by events like starquakes or tidal interactions, can generate gravitational waves with characteristic frequencies that encode information about the neutron star's internal structure. Computer simulations of neutron star interiors must account for both the quantum mechanical behavior of degenerate matter and the strong gravitational fields described by general relativity. These calculations require sophisticated numerical techniques that solve the Einstein field equations while simultaneously tracking the quantum statistical properties of neutron matter. The computational demands are enormous, requiring some of the world's most powerful supercomputers. The competition between gravity and quantum forces also determines the thermal evolution of neutron stars. Young neutron stars cool primarily through neutrino emission, as these weakly interacting particles can escape freely from the stellar interior. The rate of neutrino emission depends on the quantum properties of neutron matter, including the onset of superfluidity and the presence of exotic particles in the core. Different theoretical models of neutron matter predict vastly different cooling rates. Models that include exotic particles like hyperons or quark matter generally predict faster cooling, as these particles provide additional neutrino emission mechanisms. Models with only nucleons cool more slowly as neutrino emission becomes suppressed at lower temperatures. Observations of neutron star temperatures at different ages thus provide another way to constrain the properties of ultra-dense matter. The quantum nature of neutron star matter also affects its response to magnetic fields. In terrestrial materials, magnetic fields interact primarily with electrons, but in neutron stars, the magnetic field must interact with degenerate neutron matter itself. This leads to novel phenomena like magnetic field-induced changes in the equation of state and the possibility of magnetically driven phase transitions in the stellar core. Some theoretical models suggest that extremely strong magnetic fields, like those found in magnetars, might actually alter the balance between gravity and quantum pressure. The magnetic energy density in these objects can become comparable to the matter energy density, potentially affecting the star's structure and stability. Understanding these magnetohydrodynamic effects requires combining quantum statistical mechanics with magnetized general relativity. The study of neutron star oscillations provides another window into the quantum gravitational battle occurring in stellar cores. These oscillations, analogous to seismic waves in planets, propagate through the neutron star interior and carry information about the local pressure, density, and composition. The frequencies and damping rates of these modes depend sensitively on the quantum properties of neutron matter. Future gravitational wave detectors may be sensitive enough to observe these stellar oscillation modes directly. Different theoretical models of neutron matter predict different oscillation spectra, so gravitational wave asteroseismology could potentially distinguish between competing equations of state. This would provide an unprecedented probe of quantum mechanics operating under extreme gravitational conditions. The quantum mechanical uncertainty principle also plays a subtle but important role in neutron star physics. The zero-point motion of neutrons, required by quantum mechanics even at absolute zero temperature, contributes to the neutron pressure and affects the minimum radius of neutron stars. This quantum mechanical effect sets a fundamental lower limit on neutron star sizes that depends only on basic physical constants. As we probe deeper into neutron star cores, approaching densities that exceed nuclear density by factors of several, the quantum gravitational struggle becomes even more intense. The extreme conditions in these central regions may give rise to new phases of matter that exist nowhere else in the universe, representing the ultimate testing ground for our understanding of how quantum mechanics and gravity interact when both are pushed to their absolute limits. The victory of quantum degeneracy pressure over gravitational collapse in neutron stars represents one of the most dramatic demonstrations of quantum mechanics operating on cosmic scales. Yet this victory is only temporary and conditional, dependent on the star's mass remaining below the critical threshold where gravity finally wins. Understanding this cosmic battle between fundamental forces continues to drive both theoretical advances and observational discoveries as we seek to unravel the deepest mysteries of matter, energy, and space-time under the most extreme conditions nature can provide. At the very heart of a neutron star lies a realm so exotic that it challenges our most fundamental understanding of matter itself. Here, in a sphere perhaps just a few kilometers across, gravity has compressed matter to densities that exceed those found in atomic nuclei by factors of 5 to 10. These are conditions so extreme that they exist nowhere else in the observable universe, creating a natural laboratory where the most basic building blocks of reality are pushed beyond their normal limits. Nuclear density, the density of matter inside an atomic nucleus, represents approximately 2.3 times 10 to the 14th power grams per cubic centimeter. This is already an almost incomprehensible number, roughly equivalent to compressing all the automobiles on Earth into a space the size of a sugar cube. Yet in neutron star cores, densities can reach 5 to 10 times this value, creating conditions where the very concept of individual nucleons begins to break down. To understand what happens under such extreme compression, we must first consider what we know about the fundamental structure of matter. Protons and neutrons, the particles that make up atomic nuclei, are not truly elementary particles. Instead, they are composite objects made up of more fundamental constituents called quarks, held together by the strong nuclear force mediated by particles called gluons. Under normal conditions, quarks are permanently confined within nucleons and cannot exist as free particles. But the extreme gravitational compression in neutron star cores may be sufficient to overcome this quark confinement, leading to a phase transition where protons and neutrons dissolve into their constituent quarks. This hypothetical state of matter, known as quark matter or strange matter, would represent a fundamentally different phase of material existence, as alien to normal matter as plasma is to ordinary gas. The transition to quark matter, if it occurs, would happen gradually as density increases toward the neutron star's center. Theoretical models suggest that this transition might begin at densities around 2 to 3 times nuclear density, though the exact threshold remains highly uncertain. The process would not be a sharp boundary, but rather a gradual crossover region, where nucleons slowly lose their individual identity and merge into a soup of deconfined quarks and gluons. In this quark soup, the fundamental particles would behave according to different rules than those governing normal nuclear matter. Instead of neutrons and protons interacting through nuclear forces, we would have up quarks, down quarks, and possibly strange quarks interacting through the strong force in its most fundamental form. The pressure support against gravitational collapse would come not from neutron degeneracy, but from quark degeneracy pressure, potentially creating a stiffer equation of state that could support higher maximum masses. The presence of strange quarks in neutron star cores opens up even more exotic possibilities. Strange quarks are heavier than the up and down quarks that make up normal matter, but at the extreme densities found in neutron star cores, it might be energetically favorable to convert some up and down quarks into strange quarks. This would create strange quark matter, a hypothetical form of matter that some theories suggest might be absolutely stable, even more stable than normal nuclear matter. If strange quark matter is indeed the ground state of matter at high densities, then neutron stars might not be neutron stars at all, but rather strange stars composed primarily of strange quarks. These objects would have subtly different properties from neutron stars, including different mass-radius relationships and cooling behaviors. Distinguishing between neutron stars and strange stars remains one of the major challenges in neutron star astronomy. Another exotic possibility in neutron star cores is the formation of hyperon matter. Hyperons are particles similar to neutrons and protons, but containing strange quarks. Under the extreme conditions in neutron star cores, it might become energetically favorable to convert some neutrons into hyperons, like lambda particles, sigma particles, or Xi particles. These particles are unstable under normal conditions, but could be stabilized by the extreme densities and pressures in neutron star cores. The presence of hyperons would significantly soften the equation of state, reducing the pressure support against gravitational collapse. This creates what theorists call the hyperon puzzle. If hyperons form easily in neutron star cores, they would make it difficult to explain the existence of neutron stars with masses above 2 solar masses. Resolving this puzzle requires either that hyperons are suppressed by 3 body forces, or that other exotic physics comes into play. Kaon and pion condensation represent yet another class of exotic phenomena that might occur in neutron star cores. These are states where certain types of mesons, particles made up of quark-antiquark pairs, form macroscopic quantum condensates similar to superconductivity or superfluidity. The formation of these condensates would alter the equation of state and could have observable consequences for neutron star cooling and magnetic field evolution. The extreme gravitational fields in neutron star cores also raise the possibility that entirely new forms of matter might exist that have no terrestrial analogues. Some theoretical models suggest that color superconductivity, where quarks form Cooper pairs similar to electrons in ordinary superconductors, might develop in dense quark matter. This would create a state where the strong force exhibits phenomena analogous to the Meissner effect in electromagnetic superconductors. Temperature plays a crucial role in determining which exotic phases might exist in neutron star cores. Young neutron stars have core temperatures of around 10 to the 10th power Kelvin, hot enough that thermal effects could suppress some phase transitions. As the neutron star cools over millions of years, different exotic phases might appear sequentially. potentially creating layered structures with different types of matter at different depths. The cooling process itself depends sensitively on the composition of the core. Different exotic particles provide different neutrino emission mechanisms, leading to characteristic cooling signatures that can be observed through X-ray telescopes. Fast cooling typically indicates the presence of exotic particles that enhance neutrino emission, while slow cooling suggests a core composed primarily of nucleons. Recent observations of neutron star cooling curves have provided important constraints on core composition. Some neutron stars appear to cool faster than predicted by models containing only nucleons, suggesting the presence of exotic particles or phase transitions in their cores. Other neutron stars cool more slowly, indicating either efficient superfluidity that suppresses neutrino emission or cores that remain in the nucleonic phase. The magnetic field evolution of neutron stars also depends on their core composition. Superconducting or superfluid phases in the core would expel magnetic flux, forcing field lines to concentrate in normal matter regions. This could lead to complex field configurations and time-dependent magnetic field evolution that might be observable through changes in pulsar spin-down rates or emission properties. Theoretical studies of neutron star core composition require sophisticated techniques from quantum chromodynamics, the theory of the strong nuclear force. However, QCD calculations at high density and low temperature remain extremely challenging, even with the most powerful supercomputers available. Most current models rely on simplified approximations or phenomenological approaches that may not capture the full complexity of ultra-dense matter. Lattice QCD calculations, which discretize space-time to make the equations tractable for computers, have made significant progress in recent years, but still cannot reach the densities and temperatures relevant for neutron star cores. Alternative approaches, like effective field theories and functional renormalization. Group methods provide complementary insights, but with their own limitations and uncertainties. Experimental constraints on the properties of ultra-dense matter come primarily from heavy ion collision experiments at facilities like the relativistic Heavy Ion Collider and the Large Hadron Collider. These experiments create hot, dense nuclear matter for brief moments, allowing physicists to study the properties of quark-gluon plasma and the transition between different phases of matter. However, the conditions in these experiments differ significantly from those in neutron star cores, making direct extrapolation difficult. The study of neutron star mergers has opened a new window into core physics. When two neutron stars collide, they probe the equation of state at the highest densities reachable before black hole formation. The gravitational wave signals from these mergers encode information about how matter behaves under extreme tidal stress, providing constraints on whether cores are composed of nucleons, quarks, or more exotic forms of matter. The tidal deformability measured in gravitational wave observations provides particularly strong constraints on the equation of state at high densities. Stiffer equations of state, characteristic of nucleonic matter, produce less deformable neutron stars, while softer equations of state, expected for quark matter or hyperon matter, lead to more easily deformed stars. Current observations favor intermediate stiffness, suggesting either nucleonic matter with strong repulsive interactions or a mixture of nucleonic and exotic phases. Future gravitational wave observations promise even tighter constraints on core composition. Third-generation detectors, like the Einstein Telescope and Cosmic Explorer, will be sensitive enough to detect neutron star oscillations and potentially observe phase transitions in real time as stars are compressed beyond critical densities during mergers. The maximum mass of neutron stars provides another crucial constraint on core physics. Different theoretical models predict different maximum masses depending on the assumed composition and equation of state. The observation of neutron stars with masses around 2 solar masses rules out many soft equations of state and constrains the onset density for exotic phases. Recent discoveries of neutron stars with masses approaching 2.5 solar masses, if confirmed, would place even stronger constraints on core composition. Such massive neutron stars would require very stiff equations of state, possibly ruling out hyperon matter entirely and favoring either nucleonic matter with strong repulsive forces or a transition to self-bound quark matter at high densities. The possibility that neutron star cores contain absolutely stable strange quark matter raises profound questions about the ultimate fate of matter in the universe. If strange matter is indeed more stable than nuclear matter, then neutron stars might gradually convert to strange stars through quantum tunneling processes, though this conversion would take much longer than the current age of the universe. Some theorists have speculated about even more exotic possibilities in neutron star cores, including the formation of boson stars, crystalline quark phases, or even microscopic black holes that could exist stably within the neutron star interior. While these ideas remain highly speculative, they illustrate the vast range of possibilities when matter is compressed to densities that approach the fundamental scales of particle physics. The study of neutron star cores also connects to broader questions in fundamental physics, including the nature of confinement in quantum chromodynamics, the possibility of new phases of matter at high density, and the relationship between gravity and the strong nuclear force. Neutron stars thus serve as cosmic laboratories for testing our most basic theories about the structure of matter and the fundamental forces of nature. As observational techniques continue to improve and theoretical calculations become more sophisticated, our understanding of neutron star cores will undoubtedly evolve. Each new discovery, whether from gravitational wave detectors, X-ray telescopes, or particle physics experiments, adds another piece to the puzzle of what happens when gravity compresses matter beyond the limits of terrestrial experience. The cores of neutron stars represent the frontier where astrophysics meets particle physics, where general relativity encounters quantum chromodynamics, and where our understanding of matter under extreme conditions is pushed to its absolute limits. In these alien realms, hidden deep within collapsed stellar cores, nature may have created forms of matter so exotic that they challenge our most fundamental assumptions about the building blocks of reality itself. Neutron stars present one of the greatest observational challenges in astronomy. These objects exist in environments so extreme that no spacecraft could survive within millions of kilometers of their surfaces, and no laboratory on Earth can recreate the conditions in their interiors. Yet, remarkably, astronomers have developed ingenious methods to probe the gravitational fields of these distant objects with extraordinary precision, using techniques that transform neutron stars themselves into cosmic measuring instruments. The story of neutron star observation begins with one of the most serendipitous discoveries in astronomy. In 1967, graduate student Jocelyn Bell Burnell was analyzing radio telescope data when she noticed strange, regular pulses coming from a particular region of sky. These pulses arrived with such clockwork precision that the research team initially wondered if they might be signals from an extraterrestrial civilization, even giving the source the tongue-in-cheek designation LGM1 for little green men. The true nature of these signals soon became clear. They were observing a rapidly rotating neutron star whose magnetic field accelerated charged particles to enormous energies, creating beams of radiation that swept across space like a cosmic lighthouse. Each pulse represented one rotation of the neutron star, and the incredible regularity of these pulses immediately suggested their potential as precision clocks for studying gravitational effects. Pulsar timing represents perhaps the most precise measurement technique in all of astronomy. The best pulsars maintain timing stability that rivals atomic clocks, with pulse arrival times predictable to microsecond accuracy over periods of years or even decades. This extraordinary precision allows astronomers to detect tiny variations in the pulsar signals that reveal information about the neutron star's gravitational environment and internal structure. The basic principle behind pulsar timing is elegantly simple. Radio telescopes on Earth record the arrival times of individual pulses from a pulsar, building up a detailed record of the neutron star's rotation. Any deviation from perfectly regular timing can reveal physical processes affecting the neutron star or its environment. Changes in rotation rate might indicate internal adjustments in the star's structure, while variations in pulse arrival times could signal the presence of gravitational waves passing through the solar system. Gravitational redshift provides one of the most direct ways to measure the strength of a neutron star's surface gravity. As photons climb out of the deep gravitational well surrounding a neutron star, they lose energy and become redshifted to longer wavelengths. By comparing the observed frequencies of spectral lines from neutron star atmospheres with their laboratory values, astronomers can determine the gravitational redshift and thus constrain the neutron star's mass and radius. This technique requires extremely high-resolution spectroscopy to detect the relatively small wavelength shifts involved. Typical gravitational redshifts from neutron stars range from about 10 to 40%, depending on the star's compactness. While these shifts are large compared to those from ordinary stars, they still require sophisticated instrumentation to measure accurately, particularly given the faintness of most neutron star optical and ultraviolet emission. The Neutron Star Interior Composition Explorer, or NICER, mounted on the International Space Station, has revolutionized our ability to study neutron star surfaces through X-ray timing and spectroscopy. This remarkable instrument can measure X-ray pulse profiles with unprecedented precision, allowing astronomers to map temperature variations across neutron star surfaces and constrain their masses and radii through detailed modeling of the observed light curves. NICER exploits the phenomenon of gravitational light bending around neutron stars. The intense gravitational field curves space-time so severely that light rays follow bent paths, allowing observers to see emission from regions of the neutron star surface that would normally be hidden behind the horizon. As hotspots on the surface rotate in and out of view, the gravitational lensing effect modulates the observed X-ray flux in characteristic ways that depend on the neutron star's mass and radius. The mathematical modeling required to extract mass and radius measurements from NICER observations involves solving the equations of general relativity in the strong field regime around neutron stars. Computer codes must account for the curved spacetime geometry, the propagation of photons through this geometry, and the emission properties of matter in the neutron star's extreme magnetic and gravitational environment. The precision of these measurements approaches the level needed to distinguish between different theoretical models of ultra-dense matter. Binary pulsar systems provide even more powerful laboratories for studying neutron star gravity. When two neutron stars orbit each other, they create a dynamical gravitational environment where spacetime curvature changes continuously as the stars move through their orbits. The precision timing of pulsar signals allows astronomers to track these orbital changes with extraordinary accuracy, revealing the effects of general relativity in the strong field regime. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first compelling evidence for gravitational wave emission. As the two neutron stars orbit each other, they radiate gravitational waves that carry away orbital energy, causing the orbit to shrink at a precisely predictable rate according to Einstein's theory. The observed orbital decay matched the theoretical predictions to within a fraction of a percent, earning Russell Hulse and Joseph Taylor the Nobel Prize in Physics. More recent discoveries of binary pulsars have provided even more stringent tests of general relativity and constraints on neutron star properties. The double pulsar system PSRJ 0737-3039 AB contains two active pulsars orbiting each other with a period of just 2.4 hours. This system allows astronomers to study gravitational effects from both neutron stars simultaneously, providing multiple independent measurements of their masses and testing general relativity with unprecedented precision. The orbital dynamics of binary pulsars encode information about the neutron stars' masses through their gravitational effects on each other. Kepler's laws, modified for general relativity, relate the orbital period, eccentricity, and other orbital parameters to the component masses. By measuring multiple relativistic effects in the same system, astronomers can solve for both neutron star masses independently, providing crucial constraints on the maximum mass that neutron stars can achieve. Some binary pulsar systems exhibit orbital precession, where the elliptical orbit slowly rotates in space due to general relativistic effects. This precession rate depends on the total mass of the system and provides another independent constraint on neutron star masses. The precision of pulsar timing allows astronomers to measure precession rates of just a few degrees per year, far smaller than the relativistic precession of Mercury's orbit around the Sun. Gravitational time dilation in binary systems creates additional observable effects. The strong gravitational field of each neutron star causes time to run slower in its vicinity, affecting the observed pulse frequencies. As the pulsars move through their elliptical orbits, the varying gravitational time dilation creates periodic variations in the pulse rates that can be measured with high-precision timing observations. The discovery of gravitational waves by the Laser Interferometer. Gravitational Wave Observatory, LIGO, and its European counterpart Virgo has opened an entirely new window for studying neutron star gravity. When two neutron stars spiral into each other and merge, they generate some of the strongest gravitational wave signals detectable by current instruments. These cosmic collisions provide unique information about neutron star properties that cannot be obtained through any other observational technique. The gravitational wave signal from a neutron star merger encodes detailed information about the star's internal structure through tidal effects. As the neutron stars approach each other during their final in-spiral, their mutual gravitational attraction raises tides on each star's surface, deforming them from perfect spheres into elongated shapes. The amount of deformation depends on the neutron star's internal pressure distribution, which in turn depends on the equation of state of ultra-dense matter. Tidal deformability measurements from gravitational wave observations have provided some of the strongest constraints yet obtained on the properties of matter at nuclear density and beyond. The first neutron star merger, detected by LIGO, designated GW170817, favored equations of state with intermediate stiffness, ruling out both very soft models that would make neutron stars highly deformable and very stiff models that would make them nearly rigid. The electromagnetic counterpart to this gravitational wave event, observed across the spectrum from gamma rays to radio waves, provided additional insights into neutron star physics. The optical and near-infrared emission, powered by the radioactive decay of heavy elements synthesized in the merger, confirmed that neutron star collisions are major sites of rapid neutron capture nucleosynthesis, producing elements like gold, platinum, and uranium. Future gravitational wave detectors promise even more precise measurements of neutron star properties. Third-generation instruments like the Einstein Telescope and Cosmic Explorer will be sensitive enough to detect neutron star mergers throughout most of the observable universe, providing large statistical samples for studying the neutron star population. These detectors may also be sensitive enough to observe individual neutron star oscillation modes, opening up the field of gravitational wave asteroseismology. The measurement of neutron star moments of inertia provides another window into their internal structure. The moment of inertia depends on how mass is distributed within the star, with more centrally concentrated mass leading to smaller moments of inertia. For neutron stars, the moment of inertia is sensitive to the equation of state, particularly in the core regions where exotic phases of matter might exist. Several binary pulsar systems show evidence for geodetic precession, where the neutron star's spin axis slowly precesses due to the curved spacetime in the binary orbit. The rate of this precession depends on the neutron star's moment of inertia, providing a way to constrain the internal mass distribution. However, measuring geodetic precession requires extremely long baseline observations and careful analysis to separate it from other effects. The study of neutron star glitches provides insights into the internal structure and dynamics of these objects. Glitches, sudden increases in pulsar rotation rates, are thought to result from interactions between the superfluid neutron component in the core and the normal matter in the crust. The size and frequency of glitches depend on the amount of superfluid present and the coupling strength between different components, providing constraints on neutron star interior physics. Large glitches observed in pulsars like the Vela pulsar suggest the presence of a substantial superfluid component in neutron star cores. The post-glitch recovery behavior, where the pulsar gradually returns toward its pre-glitch rotation rate, provides information about the viscous coupling between the superfluid and normal matter components. Different theoretical models predict different recovery timescales, allowing observations to constrain microphysical properties of neutron star matter. X-ray observations of neutron star thermal emission provide another probe of internal structure and composition. Young neutron stars cool primarily through neutrino emission from their cores, with the cooling rate depending sensitively on the composition and phase transitions in the interior. Different exotic particles provide different neutrino emission mechanisms, leading to characteristic cooling signatures that can be observed through X-ray telescopes. The observation of both fast-cooling neutron stars, which appear dimmer than expected for their ages, and slow-cooling neutron stars, which remain bright longer than standard models predict, suggests a diversity in neutron star core compositions. Fast cooling typically indicates enhanced neutrino emission from exotic particles like hyperons or quark matter, while slow cooling might result from superfluidity that suppresses neutrino emission processes. Magnetic field measurements provide additional constraints on neutron star structure and evolution. The magnetic field strength can be estimated from the pulsar spin-down rate, assuming that magnetic dipole radiation dominates the energy loss. For magnetars, X-ray observations of cyclotron lines provide direct measurements of surface magnetic field strengths, reaching 10 to the 15th power Gauss. The long-term evolution of neutron star magnetic fields depends on the electrical conductivity of the interior, which in turn depends on the composition and phase structure of the core. Superconducting cores would exhibit flux expulsion and complex field decay behavior, while normal conducting cores would show different evolutionary patterns. Observations of magnetic field evolution in pulsar populations thus provide indirect probes of interior physics. Radio polarization measurements of pulsar signals reveal information about the magnetic field geometry and plasma environment around neutron stars. The rotation measure, which quantifies how much the polarization angle rotates as radio waves propagate through the magnetosphere, depends on the magnetic field strength and the density of free electrons. Changes in rotation measured over time can indicate evolving magnetic field configurations or varying plasma conditions. Recent advances in very long baseline interferometry have allowed astronomers to measure the proper motions and distances of nearby pulsars with extraordinary precision. These astrometric measurements, combined with pulsar timing data, provide independent constraints on neutron star masses and enable tests of gravitational theories in the strong field regime. The combination of multiple observational techniques provides the most powerful approach to understanding neutron star gravity and interior physics. By combining pulsar timing, X-ray observations, gravitational wave detections, and electromagnetic follow-up observations, astronomers can build comprehensive pictures of individual neutron star systems and constrain the fundamental properties of ultra-dense matter. As observational capabilities continue to advance, the precision of neutron star measurements steadily improves. Next-generation radio telescopes like the Square Kilometre Array will enable pulsar timing with unprecedented sensitivity, while improved X-ray missions will provide more detailed spectroscopic and timing observations. The synergy between these different observational approaches promises to unlock the remaining mysteries of neutron star physics and provide new insights into the behavior of matter under the most extreme gravitational conditions in the universe. In the world of theoretical astrophysics, some of the most powerful tools for understanding neutron stars are not telescopes or detectors, but supercomputers capable of performing trillions of calculations per second. These computational giants allow scientists to create virtual neutron stars, complete with their extreme gravitational fields, exotic matter phases, and complex dynamics. Through numerical simulations, researchers can explore scenarios impossible to observe directly and test theoretical predictions against the growing wealth of observational data. The challenge of simulating neutron star gravity begins with Einstein's field equations, the fundamental mathematical description of how matter and energy curve spacetime. These equations, written in the language of differential geometry, relate the curvature of spacetime at each point to the local distribution of mass, energy, momentum, and stress. For neutron stars, where gravitational fields approach their maximum possible strength, these equations must be solved with extraordinary precision to capture the physics accurately. Numerical relativity, the field devoted to solving Einstein's equations on computers, has undergone a revolution in recent decades. Early attempts to simulate strongly gravitating systems often failed due to numerical instabilities, where small computational errors would grow exponentially and destroy the calculation. Breakthrough developments in the 1990s and 2000s led to stable formulations that could evolve neutron star spacetimes for the long periods needed to study their behavior. The basic approach involves discretizing spacetime into a three-dimensional grid of points, with time evolution calculated step by step. At each grid point, the computer stores values representing the metric tensor, which describes the local geometry of spacetime, along with matter variables like density, pressure, and velocity. The Einstein field equations are then approximated as finite difference equations that relate the values at neighboring grid points. Creating accurate simulations requires careful attention to the equation of state, the relationship between pressure, density, temperature, and composition that determines how matter behaves under extreme conditions. Unlike simulations of ordinary stars, where the equation of state is well understood, neutron star simulations must grapple with fundamental uncertainties about the properties of matter at nuclear density and beyond. Different theoretical models of ultra-dense matter lead to dramatically different predictions for neutron star structure and dynamics. A stiff equation of state, where pressure increases rapidly with density, produces larger neutron stars that are more resistant to gravitational collapse. A soft equation of state leads to more compact stars with stronger surface gravity and different oscillation properties. Simulations using different equations of state thus serve as tests of our understanding of fundamental physics. The computational demands of neutron star simulations are staggering. A typical three-dimensional simulation might use grids containing millions or even billions of grid points, with each point requiring storage for dozens of variables describing the local state of matter and spacetime. The evolution equations must be solved thousands of times per second of simulated time, often requiring weeks or months of continuous computation on the world's most powerful supercomputers. One of the most important applications of numerical relativity is simulating neutron star mergers, the violent collisions that produce some of the strongest gravitational wave signals detectable by LIGO and Virgo. These simulations must capture the complex interplay between general relativity, fluid dynamics, magnetic fields, and nuclear physics as two neutron stars spiral into each other at velocities approaching the speed of light. The merger process itself unfolds over several distinct phases, each presenting unique computational challenges. During the inspiral phase, lasting many orbital periods, the neutron stars remain largely intact, while gravitational wave emission slowly drains energy from the orbit. This phase requires long-duration simulations with high accuracy to predict the gravitational wave frequency evolution observed by detectors. As the neutron stars approach their final plunge, tidal forces begin to deform their shapes significantly. The stars develop pronounced tidal bulges that grow larger as they spiral inward, eventually disrupting the stellar surfaces and ejecting material into space. Capturing this disruption accurately requires extremely high resolution near the stellar surfaces, pushing computational resources to their limits. The actual merger, when the two neutron star cores finally touch, releases enormous amounts of energy in a fraction of a second. Temperatures soar to tens of billions of degrees. Pressures exceed those in the core of the most massive stars, and matter is compressed to densities several times nuclear density. The collision generates shock waves that propagate through the merged object, potentially triggering phase transitions to exotic forms of matter. Simulating the post-merger evolution requires addressing even more complex physics. The remnant object, whether it forms a massive neutron star or collapses to a black hole, undergoes violent oscillations that generate gravitational waves at frequencies of several thousand hertz. These oscillations encode information about the equation of state and could potentially be detected by future gravitational wave detectors. The magnetic field evolution during mergers presents another major computational challenge. Neutron stars possess magnetic fields trillions of times stronger than Earth's field, and these fields become twisted and amplified during the merger process. The resulting magneto-hydrodynamic turbulence can drive powerful jets of material at near light speed, potentially explaining the gamma-ray bursts associated with some neutron star mergers. Simulating magnetic fields in numerical relativity requires solving the equations of magneto-hydrodynamics simultaneously with Einstein's field equations. This involves tracking both the matter motion and the magnetic field evolution while ensuring that the field remains properly coupled to the conducting plasma. The computational cost increases significantly, as magnetic field variables must be stored and evolved at every grid point. Nuclear physics adds yet another layer of complexity to neutron star simulations. As matter is compressed to extreme densities during mergers, it may undergo phase transitions to quark matter, hyperon matter, or other exotic phases. Each phase has different thermodynamic properties and contributes differently to the pressure support against gravitational collapse. Simulations must include realistic treatments of these phase transitions and their effects on stellar structure. The synthesis of heavy elements during neutron star mergers, the rapid neutron capture process that creates elements like gold and platinum, requires detailed nuclear reaction networks involving thousands of different isotopes. Simulations must track the abundances of these isotopes as they are created, decay, and interact with each other in the extreme conditions following a merger. This nucleosynthesis determines the composition and properties of the material ejected from the merger site. Recent advances in computational techniques have enabled increasingly sophisticated neutron star simulations. Adaptive mesh refinement allows simulations to automatically increase resolution in regions where high accuracy is needed while using coarser grids elsewhere, dramatically improving computational efficiency. Multiple coordinate systems can be used simultaneously to better handle the extreme gravitational fields near neutron star surfaces. Spectral methods, which represent functions as sums of smooth basis functions rather than discrete grid values, can achieve much higher accuracy than traditional finite difference schemes. These methods are particularly useful for simulating the long-term evolution of isolated neutron stars, where maintaining high accuracy over many rotation periods is essential for studying phenomena like magnetic field decay or thermal evolution. The validation of numerical simulations requires careful comparison with analytical solutions in simplified cases and convergence testing to ensure that results become independent of grid resolution. Mock data challenges, where simulated gravitational wave signals are analyzed using the same techniques applied to real detector data, help verify that simulations accurately capture the physics relevant for gravitational wave astronomy. Simulations have revealed many surprising aspects of neutron star physics that were not anticipated from analytical calculations alone. The discovery that neutron star mergers can produce stable, massive remnants that survive for seconds or longer before collapsing to black holes was a major surprise that required simulations to uncover. These hypermassive neutron stars are supported temporarily by rapid rotation and thermal pressure before eventually succumbing to gravitational collapse. The amount of material ejected during neutron star mergers, crucial for understanding the synthesis of heavy elements and the electromagnetic counterparts to gravitational wave events, depends sensitively on the equation of state and can only be predicted accurately through detailed simulations. Different equations of state predict ejected masses ranging from less than 1% to several percent of a solar mass, with important implications for the chemical evolution of galaxies. Simulations have also revealed the complex dynamics of magnetic field amplification during mergers. The differential rotation and turbulence generated during the collision can amplify magnetic fields by factors of hundreds or thousands, creating field strengths that approach equipartition with the kinetic energy of the fluid motion. These amplified fields can drive powerful outflows that may power short gamma-ray bursts. The gravitational wave signals from neutron star mergers encode detailed information about the underlying physics, but extracting this information requires accurate theoretical templates based on numerical simulations. Template banks containing hundreds of thousands of simulated waveforms allow gravitational wave detectors to identify merger signals and measure their properties with high precision. Each new simulation adds to this template bank and improves our ability to extract science from gravitational wave observations. Future developments in numerical relativity will likely focus on including even more realistic physics in neutron star simulations. Neutrino transport, which plays an important role in the cooling and composition evolution of merger remnants, requires sophisticated radiation transport calculations that are computationally expensive but becoming feasible with advancing computer power. The inclusion of weak interaction processes, such as beta decay and electron capture, affects the composition and thermal evolution of neutron star material during and after mergers. These processes determine the neutron to proton ratio in the ejected material and influence the nucleosynthesis yields and electromagnetic signatures of kylonovae. Quantum effects, while typically negligible in classical astrophysical simulations, might become important in the extreme conditions near neutron star mergers. Quantum corrections to the equation of state, the formation of exotic quantum phases, and the behavior of matter in ultra-strong magnetic fields represent frontier areas where simulations are beginning to incorporate quantum mechanical effects. The development of exascale computing, with machines capable of performing more than 10 to the 18th power calculations per second, promises to revolutionize neutron star simulations. These unprecedented computational resources will enable simulations with much higher resolution, longer evolution times, and more complete physics than ever before possible. Machine learning techniques are beginning to be applied to neutron star simulations, both to accelerate calculations and to extract patterns from large simulation datasets. Neural networks can be trained to approximate expensive calculations like equation of state evaluations or nuclear reaction rates, potentially speeding up simulations by orders of magnitude while maintaining high accuracy. The ultimate goal of neutron star simulations is to create a complete theoretical framework that can predict all observable properties of these objects from first principles. This requires bridging the gap between quantum chromodynamics, which governs the behavior of quarks and gluons, and general relativity, which describes gravity and space-time curvature. While this goal remains challenging, each advance in simulation capabilities brings us closer to a unified understanding of matter under extreme conditions. Simulations also serve as virtual laboratories for testing ideas about neutron star physics that cannot be explored through observations alone. Questions about the maximum mass of neutron stars, the possibility of phase transitions in stellar cores, and the relationship between different observational signatures can all be addressed through carefully designed simulation studies. The synergy between simulations and observations has become one of the most powerful tools in modern neutron star astrophysics. Simulations guide the interpretation of observational data, while observations provide crucial tests of simulation predictions. This feedback loop between theory and observation, mediated by ever more sophisticated computer simulations, continues to drive our understanding of gravity and matter in their most extreme manifestations. As we stand on the threshold of even more advanced gravitational wave detectors and more sensitive electromagnetic telescopes, the role of numerical simulations in neutron star science will only grow in importance. These computational laboratories provide our best hope for understanding the fundamental physics operating in neutron star cores and unlocking the secrets of matter compressed beyond the limits of terrestrial experience. In the cosmic hierarchy of dense objects, neutron stars occupy a precarious position between ordinary matter and the ultimate gravitational abyss of black holes. There exists a critical threshold, a maximum mass beyond which even the quantum degeneracy pressure of neutrons cannot resist the relentless pull of gravity. When this limit is exceeded, the neutron star faces inevitable collapse into a black hole, marking one of the most dramatic phase transitions in the universe and representing gravity's final victory over all other forces of nature. The theoretical foundation for this mass limit was laid in the 1930s by J. Robert Oppenheimer, Richard Tolman, and George Volkoff, who extended earlier work on white dwarf stars to the realm of neutron degeneracy. Their calculations revealed that neutron stars, unlike their white dwarf cousins, which can exist in stable equilibrium at any mass below the Chandrasekhar limit, face a more complex situation where the maximum supportable mass depends critically on the properties of matter at nuclear density and beyond. The Tolman-Oppenheimer-Volkoff limit, as this maximum mass has come to be known, emerges from the fundamental competition between gravitational attraction and quantum pressure. As mass is added to a neutron star, the gravitational field becomes stronger, compressing the interior to higher densities. Initially, this compression increases the neutron degeneracy pressure, providing additional support against further collapse. However, general relativity introduces a crucial modification to this simple picture. In Einstein's theory of gravity, pressure itself contributes to the gravitational field, acting as a source of space-time curvature, just like mass and energy. This means that the very pressure supporting a neutron star against collapse also enhances the gravitational field trying to crush it. As the neutron star becomes more massive and the interior pressure increases, this relativistic effect becomes increasingly important, eventually leading to a situation where additional pressure actually makes the gravitational collapse more likely rather than less. The exact value of the maximum neutron star mass remains one of the most important unsolved problems in astrophysics. Current theoretical estimates range from about 2 solar masses to perhaps 3 solar masses, depending on the assumed properties of ultra-dense matter. This uncertainty reflects our incomplete understanding of how matter behaves at densities exceeding those found in atomic nuclei, where the familiar rules of nuclear physics may break down entirely. Recent observations have begun to narrow this range through the discovery of increasingly massive neutron stars. The pulsar PSRJ 0614-2230, with a precisely measured mass of 1.97 solar masses, set a firm lower bound on the maximum mass when it was discovered. More recently, PSRJ 0740 plus 6620 has been measured to have a mass of 2.14 solar masses, pushing the lower bound even higher. These massive neutron stars place important constraints on the equation of state of ultra-dense matter. Models that predict maximum masses below the observed values can be ruled out, eliminating many theoretical possibilities for exotic matter phases in neutron star cores. The existence of neutron stars with masses approaching 2.5 solar masses, if confirmed by future observations, would place even stronger constraints on fundamental physics. The process of gravitational collapse beyond the maximum mass threshold is both rapid and irreversible. When additional matter is added to a neutron star that is already near its maximum sustainable mass, the transition to black hole formation can occur in milliseconds. Unlike the gradual evolution typical of most astrophysical processes, this collapse represents a genuine phase transition where the character of the object changes fundamentally and instantly. During the collapse, the neutron star's radius shrinks dramatically, while its mass remains approximately constant. The surface gravity increases without bound as the radius approaches the Schwarzschild radius, the critical size below which nothing, not even light, can escape the gravitational pull. Time dilation effects become extreme, with time appearing to slow down drastically for any hypothetical observer on the collapsing surface. The formation of an event horizon marks the point of no return in this collapse process. The event horizon is not a physical surface, but rather a boundary in space-time beyond which no causal influence can propagate to external observers. Once matter crosses this boundary, it becomes forever disconnected from the outside universe, disappearing from the perspective of distant observers due to the extreme gravitational time dilation. Neutron star mergers provide natural laboratories for studying the collapse threshold in action. When two neutron stars spiral into each other, they can temporarily form a hypermassive object whose total mass exceeds the maximum that can be supported by a single neutron star. These transient objects are stabilized temporarily by rapid rotation and thermal pressure, but must eventually collapse to black holes as they lose energy through gravitational wave emission and cool through neutrino radiation. The lifetime of these hypermassive neutron stars depends sensitively on their mass and the equation of state of matter in their cores. Objects that are only slightly above the maximum mass threshold might survive for seconds or even minutes before collapsing, while those with much higher masses collapse almost immediately after formation. This survival time affects the electromagnetic signals associated with neutron star mergers, influencing the brightness and duration of kilonovae and the properties of any gamma-ray bursts that might be produced. Observations of short gamma-ray bursts have provided indirect evidence for the formation of black holes through neutron star collapse. These intense flashes of high-energy radiation, lasting typically less than 2 seconds, are thought to be powered by jets of material launched from newly formed black holes. The association between short gamma-ray bursts and gravitational wave signals from neutron star mergers supports this interpretation and provides insights into the collapse process. The transition from neutron star to black hole involves dramatic changes in the space-time geometry around the object. The metric describing space-time around a neutron star, while strongly curved, allows light and matter to escape from the surface. The black hole metric, by contrast, contains a region where space-time curvature becomes so extreme that escape becomes impossible. This transition occurs not gradually, but as a sharp phase change when the stellar radius drops below the Schwarzschild radius. Different theoretical models of the collapse process predict different observational signatures. If the collapse occurs rapidly, any surface emission from the neutron star would be cut off abruptly as the event horizon forms. If the collapse proceeds more gradually, there might be a period of intense heating and emission as matter is compressed to extreme densities before disappearing behind the event horizon. The concept of gravitational mass limits extends beyond neutron stars to other exotic objects that might exist in the universe. Quark stars, composed entirely of deconfined quark matter, would have their own maximum mass limits that depend on the properties of the quark matter equation of state. Some theoretical models suggest that quark stars might be able to support higher masses than neutron stars, though this remains highly uncertain. Strange stars, hypothetical objects composed of absolutely stable strange quark matter, would obey different mass limits entirely. If strange matter is indeed more stable than nuclear matter, then the maximum mass for strange stars could be significantly higher than for neutron stars. However, the existence of strange stars remains purely speculative, with no confirmed observational evidence for such objects. The population of neutron stars near the maximum mass threshold provides important information about stellar evolution and supernova physics. The initial mass function of neutron stars depends on the properties of their progenitor stars and the details of the core collapse and explosion process. Understanding the distribution of neutron star masses thus offers insights into both stellar physics and the fundamental properties of matter. Gravitational wave observations have begun to constrain the maximum mass through studies of neutron star mergers. The in-spiral signals encode information about the individual masses of the merging neutron stars, while the post-merger signals can reveal whether the remnant forms a stable neutron star or collapses to a black hole. Future gravitational wave detectors with improved sensitivity may be able to observe the collapse process directly. The stability of neutron stars near the maximum mass limit can be affected by external factors such as accretion or magnetic field evolution. A neutron star that is stable in isolation might become unstable if it accretes additional matter from a companion star. This process could explain some observations of black hole formation in X-ray binary systems, where the compact object appears to have grown in mass over time. Magnetic fields complicate the analysis of maximum mass limits because they provide additional pressure support that can stabilize neutron stars against gravitational collapse. Very strongly magnetized neutron stars, known as magnetars, might be able to support slightly higher masses than their non-magnetized counterparts. However, the energy stored in such strong magnetic fields would eventually decay, potentially triggering delayed collapse to a black hole. Rotation also affects the maximum mass that neutron stars can support. Rapidly rotating neutron stars experience centrifugal forces that partially offset gravitational attraction, allowing them to support higher masses than non-rotating stars. The maximum mass for a rapidly rotating neutron star can be 20 to 30% higher than for a static star with the same equation of state. However, neutron stars cannot rotate arbitrarily rapidly because centrifugal forces would eventually overcome gravitational attraction and tear the star apart. The maximum rotation rate depends on the neutron star's mass and radius, creating a complex relationship between mass, rotation, and stability. Some neutron stars might exist in a metastable state where they are stable against collapse but unstable against spin-down that could eventually trigger collapse. The study of neutron star oscillations provides another window into understanding stability and mass limits. These oscillation modes, analogous to seismic waves in planets, have frequencies that depend on the neutron star's mass, radius, and internal structure. As a neutron star approaches the maximum mass limit, certain oscillation modes become unstable, potentially triggering collapse even if the star would otherwise be stable. Future observations will likely refine our understanding of the maximum mass limit through several approaches. Improved gravitational wave detectors will observe more neutron star mergers and provide better constraints on the equation of state. more sensitive radio telescopes will discover additional massive pulsars and extend the range of measured neutron star masses. Advanced X-ray telescopes will study the thermal evolution and surface properties of neutron stars across a range of masses. The discovery of a neutron star with a mass significantly above current theoretical limits would represent a revolutionary finding that would require new physics to explain. Such an observation might indicate the existence of new forms of matter that provide additional pressure support, or it could suggest modifications to our understanding of gravity itself in extreme environments. Conversely, the observation of a sharp cutoff in the neutron star mass distribution would provide strong evidence for the existence of a maximum mass limit and help constrain the equation of state of ultra-dense matter. The shape of this cutoff, whether sharp or gradual, would reveal information about the stability of neutron stars near the threshold and the dynamics of the collapse process. The collapse threshold represents more than just an astrophysical curiosity. It embodies the fundamental limits imposed by the laws of physics on the structure of matter and space-time. At this boundary, quantum mechanics makes its final stand against the inexorable pull of gravity, and the outcome determines whether matter can exist in stable form or must surrender to the ultimate gravitational embrace of a black hole. Understanding this threshold requires bringing together insights from nuclear physics, quantum field theory, general relativity, and observational astronomy. Each advance in any of these fields contributes to our growing knowledge of where the boundary lies and what physical processes determine its location. As our theoretical understanding improves and observational capabilities advance, we continue to probe ever closer to this fundamental limit where matter gives way to pure space-time curvature. The collapse threshold thus stands as one of the most profound boundaries in physics, marking the transition between objects that can be observed and studied directly and those that hide their secrets behind event horizons. It represents gravity's ultimate victory, the point where the curvature of space-time becomes so extreme that it overwhelms all other forces and consumes matter itself into the darkness of a black hole. In the pantheon of cosmic laboratories, neutron stars stand as perhaps the most extraordinary testing grounds for our fundamental theories of physics. These collapsed stellar cores create gravitational environments so extreme that they probe regimes of space-time curvature inaccessible to any earthbound experiment. Within their vicinity, Einstein's theory of general relativity faces its most stringent tests. Alternative theories of gravity reveal their predictions, and the very foundations of our understanding of space, time, and matter are pushed to their absolute limits. The importance of neutron stars as gravitational laboratories stems from their unique position in the cosmic hierarchy of dense objects. They are compact enough to generate gravitational fields approaching the maximum possible strength while remaining stable against collapse into black holes. Unlike black holes, whose interiors are hidden behind event horizons, neutron stars allow direct observation of matter and energy operating under extreme gravitational stress. This accessibility makes them invaluable for testing theoretical predictions that would otherwise remain purely speculative. Einstein's general relativity has withstood every experimental test devised since its formulation over a century ago. From the bending of starlight during solar eclipses to the detection of gravitational waves from colliding black holes. Yet most of these tests have probed relatively weak gravitational fields, where space-time curvature remains modest, and deviations from Newtonian gravity are small. Neutron stars operate in the strong field regime, where general relativity makes predictions that differ dramatically from those of alternative theories. The precision timing observations of pulsars provide some of the most accurate tests of general relativity ever performed. The millisecond pulsars, neutron stars rotating hundreds of times per second, maintain timing stability that rivals the best atomic clocks on Earth. This extraordinary precision allows astronomers to detect tiny deviations in pulse arrival times that reveal the effects of gravitational time dilation, space curvature, and gravitational wave emission. Binary pulsar systems offer particularly powerful tests because they create dynamical gravitational environments where space-time curvature changes continuously as the neutron stars orbit each other. The famous Hulse-Taylor binary pulsar provided the first confirmation of gravitational wave emission, with the observed orbital decay matching Einstein's predictions to within a few parts in 10,000. More recent discoveries of double pulsar systems have pushed the precision of these tests to even greater levels. The double pulsar system PSRJ 0737-3039 represents the ultimate laboratory for testing general relativity in the strong field regime. This remarkable system contains two active pulsars orbiting each other with a period of just 2.4 hours, allowing astronomers to observe relativistic effects from both neutron stars simultaneously. The system exhibits orbital precession, gravitational time dilation, Shapiro delay, and orbital decay due to gravitational wave emission, all of which can be measured with extraordinary precision. Each of these relativistic effects provides an independent test of Einstein's theory. The orbital precession occurs because the elliptical orbit slowly rotates in space due to the curvature of spacetime around the massive neutron stars. The rate of precession depends on the total mass of the system and provides a direct measurement of how matter curves spacetime in the strong field regime. Gravitational time dilation becomes measurable in binary pulsar systems because the neutron stars experience varying gravitational potentials as they move through their elliptical orbits. When a pulsar is closer to its companion, it experiences stronger gravitational fields that cause its clocks to run slower relative to distant observers. This effect creates periodic variations in the observed pulse rates that can be detected through long-term timing observations. The Shapiro delay effect occurs when radio pulses from one pulsar pass through the curved spacetime near its companion on their way to Earth. The gravitational field of the companion neutron star increases the travel time of these radio signals, creating a measurable delay that depends on the companion's mass and the geometry of the orbit. This effect provides another independent constraint on the system parameters and tests of general relativity. Perhaps most remarkably, the orbital decay of binary pulsar systems due to gravitational wave emission has been confirmed to match Einstein's predictions with incredible precision. As the neutron stars orbit each other, they generate ripples in spacetime that carry away energy, causing the orbit to shrink gradually over time. The rate of this orbital decay can be predicted exactly from general relativity and compared with decades of timing observations. The agreement between theory and observation in these binary pulsar tests is truly extraordinary. The orbital decay of the Hulse-Taylor pulsar matches the general relativistic prediction to better than 1 part in 10,000, while the double pulsar system shows even better agreement. These tests probe general relativity in gravitational fields billions of times stronger than those accessible to solar system experiments. Alternative theories of gravity face severe constraints from these pulsar observations. Many modified theories that attempt to explain dark matter or dark energy through changes to gravitational physics predict deviations from general relativity that should be detectable in strong field environments. The precise agreement between pulsar observations and Einstein's predictions rules out large classes of these alternative theories. Scalar tensor theories, which include additional fields beyond the metric tensor of general relativity, predict violations of the strong equivalence principle that should be observable in neutron star systems. These theories typically predict that the gravitational binding energy of neutron stars should affect their response to external gravitational fields, leading to orbital anomalies in binary systems. The absence of such anomalies in pulsar observations places tight constraints on scalar tensor theories. Extra-dimensional theories, motivated by string theory and other approaches to quantum gravity, often predict modifications to general relativity at high energies or in strong gravitational fields. Neutron stars, with their extreme densities and gravitational fields, provide natural testing grounds for these modifications. So far, no deviations from general relativity have been detected, constraining the parameter space of extra-dimensional models. Some theories predict the existence of additional gravitational degrees of freedom that could lead to dipole gravitational radiation, a form of energy loss not present in general relativity. Binary pulsar systems would lose energy faster than predicted by Einstein's theory if such radiation existed. The precise match between observed and predicted orbital decay rates rules out dipole radiation and constrains theories that predict its existence. The neutron stars themselves serve as laboratories for testing the strong equivalence principle, one of the fundamental assumptions underlying general relativity. This principle states that all forms of matter and energy respond identically to gravitational fields, regardless of their internal structure or composition. Neutron stars, with their exotic compositions and extreme binding energies, provide crucial tests of this principle. The gravitational binding energy of a neutron star represents a significant fraction of its total mass energy, unlike ordinary matter where binding energies are negligible. If the strong equivalence principle were violated, this binding energy might respond differently to external gravitational fields, leading to anomalous accelerations of neutron stars in binary systems. The precise orbital motion of binary pulsars confirms that neutron stars fall in external gravitational fields exactly as predicted by the equivalence principle. Different neutron star compositions would test the equivalence principle in different ways. A neutron star containing exotic matter like strange quarks or hyperons would have different binding energy contributions than a star composed purely of nucleons. Comparing the orbital behavior of neutron stars with different masses and presumably different compositions provides additional tests of the equivalence principle in the strong field regime. The moment of inertia of neutron stars provides another avenue for testing gravitational physics. General relativity makes specific predictions about how the moment of inertia relates to the mass and radius of a neutron star, predictions that differ from those of alternative theories. Measuring neutron star moments of inertia through observations of geodetic precession in binary systems could reveal deviations from Einstein's theory. Gravitational wave observations have opened entirely new possibilities for testing general relativity using neutron stars. The LIGO and Virgo detectors have observed gravitational waves from neutron star mergers, providing direct confirmation of Einstein's predictions about how space-time itself propagates disturbances at the speed of light. These observations test general relativity in the most dynamic and extreme gravitational environments ever observed. The in-spiral phase of neutron star mergers probes the two-body dynamics of strongly gravitating objects, testing whether Einstein's equations correctly predict the orbital evolution as the neutron stars spiral toward each other. The merger phase tests general relativity in the most extreme conditions, where space-time curvature reaches values comparable to those near black hole horizons. Future gravitational wave observations will provide even more stringent tests of gravitational physics. Third-generation detectors, like the Einstein telescope, will be sensitive enough to observe neutron star oscillations and potentially detect post-Newtonian corrections to the gravitational wave signal that would reveal deviations from general relativity. The polarization of gravitational waves provides another test of Einstein's theory. General relativity predicts that gravitational waves should exhibit only two polarization states, corresponding to the two independent ways that space-time can be stretched and compressed. Alternative theories often predict additional polarization modes that could be detected by networks of gravitational wave detectors with different orientations. Tests of Lorentz invariance, the principle that the laws of physics are the same in all inertial reference frames, can be performed using pulsar timing observations. Any violation of Lorentz invariance would cause the travel time of radio pulses to depend on their frequency or the direction of propagation. The extraordinary timing precision of millisecond pulsars makes them sensitive to Lorentz violation effects that would be undetectable in other systems. Some quantum gravity theories predict modifications to general relativity that become important near the Planck scale, where quantum effects on space-time itself become significant. While neutron stars do not approach Planck scale densities, they do probe energy scales and gravitational fields much higher than those accessible to laboratory experiments. Any quantum corrections to general relativity might therefore be detectable in neutron star observations. The study of neutron star populations across cosmic time provides tests of whether the fundamental constants of physics, including Newton's gravitational constant, have remained truly constant throughout the universe's history. Changes in these constants would affect neutron star formation rates, maximum masses, and cooling evolution in ways that might be detectable through surveys of neutron star properties at different redshifts. Neutron stars also provide laboratories for testing the interaction between gravity and other fundamental forces. The extreme magnetic fields of magnetars, reaching strengths of 10 to the 15th power Gauss, create environments where electromagnetic and gravitational effects become comparable in strength. Understanding how these forces interact in such extreme conditions requires precision tests that neutron stars uniquely provide. The cooling evolution of neutron stars offers insights into how gravity affects particle physics processes in extreme environments. Different neutrino emission mechanisms, some of which depend on gravitational effects, like the coupling between gravitational and weak nuclear forces, produce characteristic cooling signatures that can be observed through X-ray telescopes. Some theories of modified gravity predict that neutron stars should exhibit different thermal evolution than predicted by general relativity. These theories often include scalar fields that can affect the interaction between matter and radiation, potentially altering cooling rates or surface emission properties in detectable ways. As observational techniques continue to improve and new theoretical frameworks emerge, neutron stars will undoubtedly continue to serve as crucial testing grounds for our understanding of gravity and fundamental physics. Each new measurement of a neutron star property, whether through electromagnetic observations or gravitational wave detections, provides another data point for testing the foundations of modern physics. The unique combination of extreme gravitational fields, precise observational techniques, and long-term stability makes neutron stars irreplaceable laboratories for probing the deepest questions about the nature of space, time, and gravity. They represent natural experiments operating at energy scales and field strengths that may never be accessible to human technology, providing our best hope for discovering new physics beyond the standard model of particle physics and general relativity. In this role as cosmic laboratories, neutron stars continue to validate Einstein's remarkable theory, while simultaneously searching for hints of new physics that might guide us toward a more complete understanding of the universe. They stand as monuments to the power of precision observation and theoretical prediction, demonstrating how the most extreme environments in nature can illuminate the most fundamental laws governing reality itself. In the vast cosmic theater where galaxies spiral through space and stars are born and die in spectacular fashion, neutron stars stand as perhaps the universe's most paradoxical objects. They are simultaneously the smallest and most massive stars, the quietest and most energetic beacons, the most stable and most violent remnants of stellar death. These cosmic lighthouses pulse with mechanical precision across billions of years, while harboring in their cores some of the most extreme physics imaginable, creating a bridge between the quantum realm of subatomic particles and the grand stage of general relativity. As we reach the end of our journey through the gravitational wonderland of neutron stars, it becomes clear that these objects represent far more than mere astronomical curiosities. They are cosmic laboratories where the fundamental forces of nature are pushed to their absolute limits, natural experiments that probe regimes of physics completely inaccessible to earthbound science, and precise timepieces that allow us to test our most cherished theories about the nature of space, time, and matter. What we know about neutron stars reads like a catalogue of extremes that challenge human comprehension. We know they contain more mass than our Sun compressed into spheres smaller than cities, creating surface gravities that would flatten mountains to mere centimeters in height. We know their magnetic fields can be trillions of times stronger than Earth's, capable of disrupting atomic structure itself and launching charged particles to velocities approaching the speed of light. We know they rotate with the stability of atomic clocks, while simultaneously generating gravitational waves that ripple through the fabric of space-time. We understand that their crusts consist of crystalline lattices of exotic nuclei arranged in phases that have been playfully dubbed nuclear pasta, while their cores may harbour forms of matter that exist nowhere else in the universe. We have measured their masses with extraordinary precision using pulsar timing, mapped their surfaces using gravitational light bending, and witnessed their collisions through gravitational wave detectors that can sense distortions smaller than 1/10,000th the width of a proton. Yet for all our accumulated knowledge, neutron stars continue to guard many of their deepest secrets. The precise nature of matter at the highest densities remains uncertain, with theoretical possibilities ranging from superfluids of neutrons to exotic soups of deconfined quarks and strange matter. The maximum mass that these objects can achieve before collapsing into black holes depends sensitively on physics we do not yet fully understand, leaving open fundamental questions about the ultimate fate of matter under extreme gravitational stress. The equation of state that describes how pressure relates to density in neutron star cores represents one of the greatest unsolved problems in modern physics. Despite decades of theoretical work and increasingly sophisticated experiments, we cannot yet predict from first principles whether a neutron star with twice the Sun's mass should have a radius of 10 kilometers or 15 kilometers. This uncertainty reflects our incomplete understanding of how the strong nuclear force behaves when nucleons are compressed beyond the densities found in atomic nuclei. Future observations promise to narrow these uncertainties through multiple complementary approaches. Gravitational wave detectors will observe larger numbers of neutron star mergers, providing statistical constraints on the population properties and tidal deformabilities that encode information about internal structure. Advanced X-ray telescopes will map surface emission with greater precision, revealing details about magnetic field configurations and thermal evolution. Radio telescopes of unprecedented sensitivity will discover new populations of pulsars and measure their properties with ever greater accuracy. The next generation of gravitational wave detectors, with sensitivities improved by orders of magnitude, may be able to observe neutron star oscillations directly, opening the field of gravitational wave astroseismology. Just as seismic waves reveal the internal structure of Earth, these stellar oscillations would provide direct probes of neutron star interiors, potentially distinguishing between different phases of ultra-dense matter and revealing the presence of exotic particles or phase transitions. Perhaps most intriguingly, future observations may detect the boundaries where neutron star physics transitions into even more exotic regimes. We may witness the formation of quark stars, observe strange matter in neutron star cores, or detect signatures of quantum phase transitions that occur nowhere else in nature. Each new discovery will add another piece to the puzzle of understanding how matter behaves when compressed beyond the limits of terrestrial experience. The role of neutron stars in advancing fundamental physics extends far beyond their use as laboratories for studying ultra-dense matter. They serve as precision instruments for testing general relativity in regimes where space-time curvature approaches its maximum possible values, while still allowing stable matter to exist. The extraordinary agreement between pulsar timing observations and Einstein's predictions has validated general relativity in strong field regimes and constrained alternative theories of gravity. As we search for new physics beyond the standard models of particle physics and cosmology, neutron stars will undoubtedly continue to play crucial roles. They may reveal evidence for extra dimensions, quantum corrections to general relativity, or violations of fundamental symmetries that could guide us toward more complete theories of nature. The precision of pulsar timing observations and the extreme conditions in neutron star cores make them sensitive to effects that would be completely undetectable in any earthbound experiment. Neutron stars also represent a remarkable convergence of different fields of physics, bringing together insights from nuclear physics, quantum field theory, condensed matter physics, plasma physics, and general relativity. Understanding these objects fully requires bridging the gap between the quantum mechanical behavior of individual particles and the macroscopic properties of stellar objects, connecting the microscopic world of quarks and gluons to the cosmic scale of space-time curvature and gravitational waves. The study of neutron stars has already led to numerous unexpected discoveries that have reshaped our understanding of physics and astronomy. The discovery of pulsars themselves was completely unanticipated, revealing the existence of cosmic lighthouses with timing precision that surpasses our best atomic clocks. The observation of binary pulsars provided the first evidence for gravitational waves decades before their direct detection, earning Nobel Prizes and validating one of Einstein's most abstract predictions. More recently, the detection of gravitational waves from neutron star mergers has opened the era of multi-messenger astronomy, allowing us to study cosmic events through both gravitational and electromagnetic radiations simultaneously. These observations have confirmed that neutron star collisions are major sites of heavy element synthesis, solving long-standing puzzles about the cosmic origins of gold, platinum, and other precious metals. Each neutron star merger we observe adds to our understanding of how these events shape the chemical evolution of galaxies and contribute to the cosmic abundance of elements essential for planet formation and life. The gravitational wave signals from these mergers encode information about the equation of state of matter at nuclear density, providing constraints that complement laboratory experiments and theoretical calculations. As we look toward the future, neutron stars will likely continue to surprise us with unexpected phenomena and new physics. The extreme conditions in their cores may give rise to phases of matter that we have not yet imagined, while their magnetic fields and rotation may create plasma physics phenomena that challenge our current understanding. The interaction between quantum mechanics and general relativity in these extreme environments may reveal new insights into the long-sought theory of quantum gravity. The precision timing capabilities of pulsar arrays may eventually allow us to detect the gravitational wave background from the early universe, providing a new window into cosmic history that complements observations of the cosmic microwave background. Neutron stars may thus serve not only as laboratories for studying extreme physics, but also as instruments for exploring the deepest questions about the origin and evolution of the universe itself. Perhaps most remarkably, neutron stars embody the profound connection between the largest and smallest scales in physics. These objects, with masses comparable to stars and sizes comparable to cities, are governed by quantum mechanical effects that operate on subatomic scales. The Pauli exclusion principle, a purely quantum phenomenon involving the behavior of individual fermions, determines the structure and stability of objects containing more matter than our Sun. This quantum gravitational interplay represents one of the most striking examples of how the microscopic and macroscopic worlds are interconnected in nature. Neutron stars demonstrate that quantum mechanics is not just a theory for describing atoms and molecules, but a fundamental principle that shapes the cosmos on astronomical scales. They stand as monuments to the unity of physics, showing how seemingly disparate phenomena are connected by common underlying principles. The quiet precision of pulsar signals arriving at Earth with clockwork regularity across distances of thousands of light years provides a constant reminder of the extraordinary stability and predictability that can emerge from the most violent and chaotic processes in nature. These beacons sweep across space with lighthouse-like regularity, each pulse representing a complete rotation of a neutron star spinning hundreds of times per second while maintaining timing precision that rivals our best atomic clocks. In their role as cosmic timekeepers, neutron stars serve as both clocks and beacons in the warped fabric of space-time. They mark the passage of time with extraordinary precision while simultaneously demonstrating how gravity can bend and distort the very flow of time itself. Each pulse that reaches Earth has climbed out of a gravitational well so deep that its wavelength is stretched by the journey, carrying with it information about the extreme conditions near the neutron star's surface. The legacy of neutron stars extends beyond their contributions to fundamental physics and astronomy. They represent one of humanity's greatest intellectual achievements, demonstrating our ability to understand and predict phenomena occurring under conditions so extreme that they challenge the very limits of physical theory. From the theoretical prediction of their existence in the 1930s to the detection of their gravitational wave signals in the 21st century. Neutron stars have driven advances in both theoretical understanding and observational capability. As we stand at the threshold of even more advanced gravitational wave detectors, more sensitive radio telescopes, and more powerful X-ray observatories, neutron stars will undoubtedly continue to reveal new secrets about the nature of matter, energy, space, and time. They remain our best natural laboratories for studying physics under extreme conditions, our most precise clocks for testing theories of gravity, and our most promising sources of information about the behavior of matter at densities that may never be achievable in terrestrial experiments. In the end, neutron stars represent both the triumph of theoretical physics in predicting their existence and properties, and the ongoing challenge of understanding all the mysteries they continue to present. They are products of stellar death that give birth to new insights about the nature of life and matter in the universe. They are the quiet titans of gravity, spinning silently through space while harboring in their cores some of the most extreme and exotic physics imaginable. These remarkable objects will continue to serve as beacons of discovery, guiding us toward deeper understanding of the fundamental laws that govern our universe. In their precise pulses and extreme physics, we find both answers to long-standing questions and hints of new mysteries yet to be unraveled. They remind us that even in the vast cosmos, precision and beauty can emerge from chaos and violence, creating natural laboratories where the most profound secrets of physics await discovery. The story of neutron stars is far from over. As our observational capabilities advance and our theoretical understanding deepens, these cosmic laboratories will undoubtedly reveal new phenomena that challenge our current knowledge and point toward even more fundamental truths about the nature of reality itself. In their quiet spinning and precise timing, neutron stars continue to whisper the secrets of gravity, matter, and space-time to anyone patient enough to listen to their cosmic song.